But once we return to in-person teaching, it will be on the board. So then in that case, it won't be easily, you have to take the notes yourself. But still, I would say that taking notes is a good way to learn, at least for myself, because it makes you think while right? So the speed is more suitable for thinking. All right, so let's quickly have a recap of what we talked about last week. Linear model, right? The key thing is we introduce the matrix form of a linear model that can make a lot of calculations much more easily. So if you are not familiar with the matrix form, my suggestion is to try to repeat some of the derivations yourself, and then you can see how it was done. So I think this is the most important thing. And just a quick recap that we talk about this beta hat, which is a p-dimensional estimate of the p-dimensional coefficient vector we call beta. So the linear model is written as y equals x beta plus epsilon. So beta is our so-called parameters of interest. And we showed that this beta hat is unbiased, and we showed that this is its variance, right? The variance under the setting we discussed, the so-called fixed design setting, in which we don't consider the design matrix X n by p to be random. So once it's fixed, then it can appear in the variance term. So we will have sigma squared times this inverse of X transpose X. And this term is p by p. So sigma squared is a scalar. And we also said that sigma squared, which is the variance of the error term, is what we call a nuisance parameter. By being a nuisance parameter, it is something we need to specify the model. So the model can be fully specified, but it is not our parameter of interest. So therefore, in a model, like a parametric model, linear model is a parametric model. So everything can be specified by parameters. We have parameters of interest, our beta, and a nuisance parameter, sigma squared. Okay, so last time we stopped here. We said that there is an asymptotic theory to give us this asymptotic normal distribution. So even though this class is not focusing on asymptotic theory, I'll just quickly say that the foundation for such derivation is what you have learned before, the central limit theorem. So that is the cornerstone of everything. And in this case, with this asymptotic distribution, what we gain, in addition to the mean, which is beta hat has expectation as beta, and the variance is, besides this mean and variance, we also know the form of the distribution. So what this implies, I'll continue writing, implies that beta hat is approximately normally distributed, and this is p-dimensional, with mean as the true parameter beta, and the variance covariance matrix as sigma squared times X transpose X inverse. So this is what we gain from this asymptotic theory. So by having this normal distribution, what we can say is that the estimate beta hat we get from one data set, right? The data set we have at hand is very close to beta, because normal distribution is known to be concentrated on the center. So like I said, I think 2 classes before, 95% of a chance it is one-dimensional normal distribution. You are within 2 times the standard deviation of the mean. So that is considered to be highly concentrated. And it's also called light tail distribution. So its center is the true value you hope to gain. And this is how the different estimates of beta hat, like beta hat has p elements, right? For the p covariates or p predictors. So their corresponding beta hats estimate are not necessarily uncorrelated. This is one thing. So if you think about beta hat J and beta hat K, which are the estimates for 2 predictors, J and K. If we think about their covariance, right? Each is a scalar random variable, so their covariance is a scalar. Then this can exactly be obtained from this covariance matrix, which is the JK element of this. Okay, and we should also bear in mind that sigma square, as I said, is a nuisance parameter, so we don't observe it directly. So in this case, the best we could do is to use sigma hat square, our estimate for the nuisance parameter. This is what we did last time. We try to derive that if you directly use the sum of residual squares divided by n, this one, which we call the maximum likelihood estimate for sigma square, it is unfortunately biased. So you don't get expectation equal to sigma square. It differs by a factor. So therefore, to get an unbiased estimate of sigma square, we should divide the sum of residual square by n minus p instead of n. And so basically here, we could plug in this unbiased estimate to represent the unknown true value. And similarly, we will use that here. So essentially, this tells us that the estimates for two different predictors are not necessarily uncorrelated. So this covariance term might not be zero. Depends on this element. And this element depends on how the design matrix X is like. So I can tell you that if this design matrix has columns that correspond to different predictors highly correlated, then you can actually show that by doing this inverse, you would have non-zero elements off diagonal. And that will indicate these estimates themselves are correlated. So what does this mean? Covariance being non-zero. For example, if the covariance is positive, it indicates that if my beta hat J is larger than my true beta J, then being positively correlated, it will indicate that the deviance of beta hat K from the true value beta K can also be positive. It's more likely to be positive. So they both deviate in the same direction. So this is something we should get out of this result. And as I said, when we talk about inference for a parameter, we're not just aiming to get beta hat, because that's what we call point estimate, okay? So I'll just write this again. It's just one vector. But in statistics, when we say inference, we want to know the distribution of beta hat, which is something we got here approximately, so that we can use the distribution to say more about beta given beta J, right? So what is the beta, where is beta likely to be? So we want to say that. So therefore, for inference, we need distribution of beta hat. And this is the most important thing that differs statistics, inference from, in other related fields in computer science, you also try to obtain point estimates by some optimization. So that's the biggest difference. So here the question is, if we are particularly interested in, let me just say question one. Question one, if we are particularly interested in the effect of one predictor, okay, how do we do inference for beta J? So this is effect size, or should I say effect size? Maybe I will not say it for now, because this term has this kind of narrow meaning in many contexts. So I will say beta J is the effect of predictor J on the response. So it's often the question we want to ask. For example, the effect of income or of education level on income. So in this case, to set up an inference problem, there are two ways to do it. So we'll talk about one way, but there's another way that can be done equivalently. One way is to do a hypothesis testing. So this way turns the question into a binary question. That is, I'm comparing a null hypothesis where I set beta j to be 0 versus an alternative hypothesis where we set beta j to be not 0. So in this binary question, we're just interested in knowing beta j being 0 or not, right? So it's not like we're interested in the particular value of beta j, but we just want to reject this null hypothesis so we can say, okay, qualitatively, beta j has a non-zero effect. So in this case, how do we construct a test statistic to really help us decide or to reject or not the null hypothesis? So the commonly used one is the so-called t-statistic. So t-statistic by name is some statistic whose asymptotic distribution under the null hypothesis follows a t-distribution. So that's why it's called t-statistic. In particular, if you want to understand it in the high level, because we have also two sample t statistic in another two sample comparison setting, right? But I can tell you that there is some equivalence between the two sample t test and the linear model. So essentially what we can say is that if you reformulate the two sample t test question as a way to say, oh, I have my sample as a two-level factor to indicate a group. And then we want to see whether this group has any effect on the mean. So essentially, you can write the two-sample t-test as a special case of a linear model. So Bradley, there's a question, a hand.
Yeah, I had a question about the result of the distribution of beta hat. Is that for both the fixed effects and random effects, or
No,
not random design, or
no.
just for one of them?
Just for one of them. I think for random design, you need to have an expectation around this, because the eggs will become random, right? So you need to have expectation. That's the major difference.
Right.
Yeah, thank you. Okay, so for t statistic on a high level, the t statistic, like I said, can be considered at, sorry, I think I'm teaching two classes. Maybe I said in the other class, can be considered as a standard normal random variable divided by a chi-square random variable with degrees of freedom df divided by df, and then take square root. So, and you need to have this standard normal independent of this chi-square. So as long as you have two such random variables and they're independent, and you can write this statistic as the ratio in this way, then this one would follow a so-called t distribution with degrees of freedom df. So this is the general setup. And you can actually show that for the two sample t statistic and the thing we'll present here, they can be formulated in this way, at least asymptotically. So what I'm saying here is that for this specific case, so this is the general form. Okay, I'll just say that. This is the general form. And specifically, we can write t in our case as so-called beta hat j, our estimate for predictor j, divided by its standard error. Okay, and what's the difference between standard error and standard deviation? I know it's just two ways of saying something very similar. So in my understanding, people say standard error when they are referring to a parameter estimate, and you should have the unknown parameters replaced by their plugin estimate. So in our case, if we want to say standard deviation of beta j hat, then we should look at the jth diagonal entry of this sigma square times x transpose x inverse. So we should keep the true value sigma square and then take the square root of that diagonal entry. But since we're using sigma square hat instead of sigma square, we typically call this standard error. So we already use the plugin, so it is something we can compute. So in this case, we can show that both numerator and denominator are random, right? Because if you think about it, this is beta j hat itself is random since it depends on our data x, y. And y is a random vector because epsilon, the error term, is random. And here, standard error is actually a square root of sigma square hat x transpose x inverse jth diagonal element. And we're taking the square root of that and then put that as the denominator. Okay, and because sigma square hat is random, so we also have random in our denominator. So something important to show is that, which we will actually do, is to show that beta hat and our residual, the E vector, remember that we have E1 to En as the residual vector, that they are independent, which is something I will show very soon. Because of that independence, and sigma square hat only depends on E1 to En, you essentially have independence between beta j hat and sigma square hat. And then you can satisfy this independence in the T statistic definition. And we can also have that sigma square hat subject to some scaling is chi-square distribution. That's something we showed last time, right? Based on the chi-square distribution, we have that the degrees of freedom for sigma square hat is n minus p instead of m. So therefore, you have chi-square degrees of freedom n minus p. And here, for the numerator, you have something normally distributed because we already said that asymptotically is normal. So that's why you can say asymptotically, this t follows T distribution with n minus p degrees of freedom. And I must say one more thing, that we only need to step back and saying this holds asymptotically when our error term, epsilon, is not assumed to be normally distributed. So if we want to be less stringent, we just say, oh, error terms have mean zero and finite and the common variance sigma squared. So under that more loose setting, we need this central limit theorem and asymptotic theory to say this T statistic follows T distribution asymptotically. But if we're assuming a stronger thing, that is what we wrote before, the error terms are just normally distributed, independent, common variance sigma squared, then this result will be exact. We won't need this asymptotic statement. I don't know if that makes sense to you. So basically, what we need for our result depend on, or I would say, depending on our condition, then we can say our result in a different way, maybe a stronger way and or a weaker way. But just to clarify, when we say asymptotically in this whole class, we are under the setting that our P, number of predictors, fixed. So we know what are the predictors beforehand, but we are letting sample size n go to infinity. That is, we are expecting more and more observations, so we can do better and better with our parameter estimate. And even though we can have that as n goes to infinity, beta hat is approaching beta. And that result is what we call consistency in statistical theory. That means that we hope as our sample size goes to infinity, in the ideal extreme, we would capture the whole population. That is, when our sample size is just equal to the population size, then beta hat should just be equal to beta. That's our hope. But this asymptotic distribution captures what would behave once we are given any n, right? As long as n is large, how far away is beta hat from beta? And we're capturing that deviation using the asymptotic distribution. So you can say that we can see that we scale this difference by root n, and as n increases, we are actually multiplying a larger factor to increase the difference as a way to stabilize into a distribution that does not depend on n. But as you can see that n increases, basically this factor becomes larger and larger, indicates that this difference is becoming smaller and smaller. So that's where the stabilization happens. Okay, so any questions before I continue? So the next thing I hope to show you is the independence. Okay, so why is beta j hat independent of sigma square hat? That can justify the t distribution. So with this result, in reality, to decide whether you reject the null hypothesis or not, what you did is very standard. Given your data, you compute this t statistic value, and then you look at where this value is located in this t n minus p distribution. Report is tail probabilities in both tails. So you add up the two tail probabilities, or you just look at one tail probability, multiply that by 2. And that is what you call as the p-value, right? So basically it is the probability that under the null hypothesis, your t statistic is at least as extreme as or more extreme than your observed value. So in this case, we are comparing the absolute value of this t statistic value because we care about both sides. It's a two-sided test. And then we get the two-tail p-value. We compare that to our preset significance level, for example, 0.05. And if it's less or equal than that, we said, oh, at that significance level, we reject the null hypothesis. So we should bear in mind that the rejection decision always depends on our null hypothesis and our test statistic, its null distribution, and the significance level. So we need those 4 components to make one decision. As you change your significance level, which is kind of your tolerance level for type 1 error, your decision, your binary decision may change. So this is another way to show that the statistical analysis and our decision is always subjective. So the subjectiveness can be in multiple aspects, including null hypothesis setup, your model specification, and your significance level, and your test statistic choice. Because if you choose a different test statistic, you may also get a different result. So that is something we should bear in mind. And therefore, because we can control the type 1 error for each test statistic, then what it matters is to compare the power of different test statistics to see which one is more powerful. That means if the alternative holds, can you really reject the null to identify the alternative? So that's the whole idea. And as this is a graduate level course, I was being really quick about this whole hypothesis testing setup. But I wonder if you have any questions. If you do, please just let me know anytime. Okay, so we will continue with this test statistic and try to justify that we have independence. So the next thing is to show that we have beta j hat independent of sigma square hat. Okay, so to show that, essentially, we want to show it is sufficient to show that beta hat, this vector as a whole, is independent of the residual vector E. So now we are under this normal distribution setting to make things simpler for us. So here we will just assume that in the model y equals x beta plus epsilon, we have epsilon follows an n-dimensional normal distribution with mean 0 and sigma square I. Okay, so this I is n-dimensional. So to show that, we will use the result we already have, and it's more like a review here. So we already have from the previous lectures that beta hat is what? It's the formula we'll use again and again. X transpose X inverse X transpose Y. Okay, and this means that we are having a matrix multiply to Y. And as based on the model, we would have Y as an n-dimensional vector follows a normal distribution with mean X beta and covariance sigma square I. This is what we know for Y. And for such a multi-dimensional, n-dimensional normal random variable, if we multiply it by a fixed matrix, so this is an n by t matrix, okay? Let's multiply to it. We can show that this result is still a normal random variable, normal random vector. Okay, so essentially we can show that this will follow a normal distribution with a mean. I just put a mean here as X transpose X inverse X transpose times X beta. So the mean here. And the covariance matrix would be what we have. So I just write it. Sigma square X transpose X inverse. So in other words, we already saw this result, right? So this is normal distribution beta mean and sigma square X transpose X inverse. Okay. And one more thing is about the error term, E. E is what? So this one, you know, it is Y minus X beta hat, residual. And we can put in beta hat, if you remember our definition of the hat matrix last time. So this is what we'll show again. So this is X times X transpose X inverse X transpose Y. Okay, and this is what we call the hat matrix. In other words, this residual vector is identity minus hat matrix times Y. And it's also a normal random vector. So now to show the independence between beta hat and E, we can actually use the fact that since they are, if we stack them together, if we stack beta hat and E as a two n-dimensional vector, we can still show that it is jointly normal because they both have Y involved. Okay, because of this, then this is a very important result to show for such normal setting. That is, this joint normal distribution implies that if beta hat is independent of residual vector, it is equivalent to show that covariance matrix of beta hat and E, it is a zero matrix. Okay, so this is n-dimensional, this is n-dimensional, so we will have an n by n zero matrix. So as long as we can show this zero covariance, it is equivalent to say that they are independent. And this is a nice property about joint normal distribution. All right, so then what remains for us is to show this covariance being zero matrix. So let's take a look. Oh, I think I made a mistake. Sorry, it's P by M because beta hat is P dimensional, E is N dimensional. And also here, this should be P plus M by 1 dimensional. Okay. So to show this covariance matrix, we will again use what we know already about the definition of beta hat and E. All right. So as we know that beta hat is this matrix X transpose X inverse times X transpose times Y. All right. And E is I minus H times Y. So I just write it. X transpose X inverse X transpose Y. This is our beta hat. And the second one is I minus H times Y. That's my E. And this is another property about this covariance matrix, as they both involve the same random vector Y. And the left multiply matrices are fixed. Okay, H hat matrix is also fixed because it's only about design matrix. Of course, identity matrix is fixed. So essentially, we can show that this is equal to the left matrix X transpose X inverse X transpose times the variance covariance matrix of Y itself, the n-dimensional covariance matrix of Y, times this thing, I minus H. We should have the transpose, but because of the so-called idempotency, or not, it's a symmetry, symmetry of I minus H, its transpose is itself. So I put I minus H here. Okay, now you see, as this variance covariance matrix of Y is simple, it's just sigma squared times I. Then we basically just have a scalar. We move it beforehand, and we just have the sigma square times this whole thing, X transpose X inverse times X transpose. I'll open up this multiplication times I. So I just keep it as is, plus X transpose X inverse X transpose times H. And then I'll put H back. This is H. That is X times X transpose X, X transpose. Minus, sorry, not plus, minus. And then you can see that I have cancellation, right? So I can cancel out one copy of X transpose X. This will be canceled. Then I have the same thing minus itself, and that gave me 0. So this is how we show that the covariance between beta hat and residual E is 0. And this justifies beta hat being independent of E. And this further gives us beta hat is independent of the sigma square, as sigma square is only relying on the residual vector. So this is a very important result. This independence is necessary for the T distribution of our T statistic. So coming back out of the theory here, we'll just say that the T statistic in practice is what we use to decide whether a particular predictor J has any effect on the response. Okay, so this is for testing one predictor. Do we have any questions so far? If not, then we will continue with a multi-dimensional case. So, oh, sorry, I should come back to this one to say, okay, way 1 is hypothesis testing. I haven't said my way 2 yet. Way 2 is to do inference, is to construct a confidence interval. Okay, for beta J. And as I said, that our whole class here is under the frequentist paradigm. I think I said in lecture 1. And confidence interval, p-value are both concepts under the frequentist paradigm. That means we consider the test statistic to be random. We consider the parameter of interest beta to be fixed. And by being random, we're thinking about potential data sets besides our current data set. All right, so confidence interval under the frequentist paradigm is one of the most confusing concepts, I would say. And the confusing part is the interval will be constructed from our data. Beta J is some unknown fixed quantity. And this interval, as long as it's data-based, right? So if we assume that data is random, we can have potential data sets, then essentially on each potential data set, we use our way to construct the interval, and the interval will be different. So in the frequentist paradigm, we're thinking of confidence interval as a random interval. And when we say 95% coverage of beta J, we're thinking about these potential intervals collectively. It is not the particular interval we obtain for our data set. So that is the most important part or confusing part. That is, even though you only see one interval, but the 95% probability is about potential intervals you don't directly observe. So therefore, this 95% is about the way we construct the interval, not the particular interval in our data set. Okay, and the orthogonal concept in Bayesian statistics is the so-called credible interval. And in that case, even though it's not the focus of our course, I'll say that in that case, in Bayesian inference, you fix your data. You are conditional on your data, and you consider beta J to be random. So in that case, that interval is what you're looking at. You're looking at your conditional on, and you're thinking about beta J's distribution given your data set. And for credible interval, you can say, yes, beta J has 95% chance to be lying in my interval, but you cannot make the same statement for frequentist statistic. And I think that is the most confusing part that have confused a lot of our undergraduate students in our intro to stat course. But hopefully our graduate students can clarify these concepts. And the key difference is, what do you assume as random? The interval itself or the parameter, the true parameter value? Which one do you assume as random? Anyway, coming back to a confidence interval here, essentially our construction will be based on this distribution of beta J hat. So I'll just drop this asymptotic notation by saying that we assume beta j hat follows a normal distribution with mean beta j, and sigma square hat x transpose x inverse this matrix j element. Okay, so that's the variance term. So essentially, we will construct our confidence interval based on this distribution. And if I just want to say the 95% confidence interval would just take this form. That is beta j hat plus minus 1.96 of this, of the square root of this sigma square hat x transpose x inverse j's diagonal element square root. That's it. So essentially, you can see why I said this interval is random, because beta j hat is random, sigma square hat is random, right? So therefore, you have a random interval. So essentially, people can make decision in two ways. Given a significance level 0.05, if you are doing this wave one hypothesis testing, you will need to compute the p-value for your test statistic, compare that to 0.05 to make a binary decision. Do I reject the null that beta j0? Equivalently, you can construct a 95% confidence interval and then see whether this interval overlaps with 0. If it does, then you will say, oh, I do not reject the null hypothesis. If it does, then you say, I reject null hypothesis. So in that case, these two ways are equivalent. But some people prefer the confidence interval approach because they can see more information, like confidence interval length, where the center is, how large the interval is, while for the p-value, it's just one number between 0 and 1. So it's less, how to say, informative in too many people's opinion. All right, so that's what I want to say for testing one predictor. So, and that is the question one, inference for one predictor J. So what if we are interested in more than one predictors? I call that question two. So in this case, I would divide my beta vector into two subvectors. Beta 1, beta 2. All right. And I would just assume that beta 1 has P1 dimensional, beta 2 has P2 dimensional dimensions with P1 plus P2 equal to P. They add up to my P dimensions. And correspondingly, I would have an estimate, right, beta hat. So we will write that first. So corresponding to this parameter vector beta, I have beta hat divided to beta hat 1, beta hat 2. Their dimensions match. And given that I already know my beta hat variance covariance matrix, which is P by P, right? This is something we know as sigma square x transpose x inverse. We can also divide it blockwise to reflect the two subvectors. In other words, I can write it as the variance covariance matrix of beta 1 hat only, variance covariance matrix of beta 2 hat only, and in the two off-diagonal blocks, it will be their covariance. So this will be covariance beta 1 hat, beta 2 hat. And this will be covariance matrix beta 2 hat, beta 1 hat. And we can show they're the same by the symmetry of the covariance operation. But we may have like a transpose here. Okay. So one thing to say here is that question is, if we are interested in whether the P1 predictors in my subvector 1 jointly has any effect on my response, that's the question we want to study. So, or maybe I will say beta 2, the second subvector. So the null hypothesis is just beta 2, the P2 dimensional vector is a 0 vector, P2 dimensional. And the alternative is that it is not. Okay, and when the alternative holds, what it means is sum of the coefficients in beta 2 is non-zero. And these coefficients corresponding predictors should have some effect. So can you think about, question for you to think for 10 seconds. Can you think about one scenario where you might be interested in testing the subvector being 0 as a whole instead of just one element being 0? What would be such application scenarios? And I would like to have a volunteer. I'll just wait. If not, then I'll provide my answer. And you can think about whether that makes sense to you.
Perhaps when you're trying to see whether adding additional covariates adds explanatory power to a model.
Okay, so in your explanation, why is adding an additional covariate or predictor means we need to look at a subvector?
Because if you have a certain model already specified and you're adding additional parameters to it, can
Yeah.
actually end up overfitting the model in a way where it doesn't actually add any additional information to the model. When you look at sort of adjusted R squared versus just straight up R squared, you can have an instance where you'll mechanically increase one, you just mechanically increase R squared, but you should penalize yourself
Mhm.
in the model for adding additional predictors. That's what adjusted R squared is for. And so
Yeah.
if you add too many predictors and you're overfitting the model, your adjusted R squared will actually start falling after a certain point.
So are you talking about that you're saying that the predictors corresponding to beta 2 are the ones you added as additionals?
Yes.
Okay, yeah, thank you for your answer. So basically, you're talking about the setting that you are not just adding one more predictor or covariate, but you're adding a bunch of them, and you want to know whether they together contribute anything meaningful. Yeah, that's a good explanation. Another thing I can think of in application is that suppose you already have many predictors in your model, right? P predictors, and some predictors means something similar. For example, you may not necessarily know which is the best predictor to represent education level as a factor you're interested in. Then you may consider different ways to describe the education level of one person. So you are not combining them into one predictor, but you keep them as separate predictors. Then the question is, if your question is whether education has anything influential on your income, then you want to consider those education-related predictors as a whole thing, and you can call them beta 2. Okay, so that's another setting where this could be helpful. Thank you for the answer. So to answer to have design a test for such a null hypothesis where you have a vector, right? Vector specification under the null, then there's a classical test called Wald test. Okay, so the Wald test is named after how to say early stage pioneering statistician called Abraham Wald. And he has many interesting stories. I think one particular story you might have heard of is during the Second World War. He actually, as a statistician, the question is which parts of the airplane in the war, right? War airplanes are fragile. So then they study the planes that return from the war and look at where they have holes from the bullets. And so his question, so basically there's like a selection bias, a survival bias, survivor bias issue here, because people might think, oh, where the holes are the fragile part. But he said that sharply, he pointed out that, oh, as long as this plane's returned, it means that where they were damaged, the holes were not the fragile part, and we should protect the rest part. Yeah, so I think this is a very famous saying, very famous example of survivor bias. But unfortunately, he died at a very young age, I think maybe only 40 years old, because of an airplane crash. So despite his short life, he made many important contributions. One is the Wald test. So how do we define a Wald test? You can consider this to be a generalization of the t-test or t-statistic. So the Wald statistic can be considered a multivariate version or matrix form of the t-statistic. That is, we have like a square form of the, how to say, parameter estimate, beta hat, okay? We want to create, and this is called W for Wald, and we want to create a scalar statistic value, okay? So therefore, the quadratic form will be beta 2 hat transpose. This is 1 by P2. And we want the time itself, beta 2 hat. This is P2 times 1. But just as the t statistic, we want to normalize its variance term, right? So for the scalar value without a scale, so for the scalar value case, if we don't do the square, we just divide by standard error. But once we square it, we need to divide by variance. So similarly, dividing variance here will become multiplying the inverse of the variance covariance matrix in the middle. So in this case, in the middle, we would multiply the estimated variance covariance matrix of beta 2 hat, its inverse. That's it. And this is P2 by P2 matrix. So that's why you can see that the product will be a scalar, 1 by 1. All right, and I can say that if this P2 is just one-dimensional, it reduces to our t statistic. This W would become just the square of the t statistic. Okay, and the asymptotic distribution, I'll just quickly say that. Just like the t distribution is like, how to say, t distribution is like normal distribution, and maybe I'll just write here. So normal, standard normal distribution versus t distribution, n by p. This can be analogous in a very, how to say, loose way. I would say analogous. So this is the not squared form, and this is the squared form. In the square form, this normal thing will give us like a chi-square thing, and this t thing, t distribution will become an f distribution thing. So this is what I'm trying to say, that the t distribution and f distribution, their relationship is similar to the relationship between a normal distribution and a chi-square distribution. So based on this very high level intuition, we can guess that since our t statistic follows t distribution, maybe this Wald statistic will follow the f distribution. And chi-square distribution has just 1 degrees of freedom, all right? So basically, this degrees of freedom depends on what? Depends on how many independent normal random variable square you add up to create a sum, and that follows the chi-square. So the degrees of freedom in the number of independent normal random variable will be reflected here. For f, you need 2 degrees of freedom. So one is kind of similar to the degrees of freedom chi-square. How many independent things you add up as in the numerator of t, right? Because in the numerator of t, you have standard normal. But you also in f to carry the degrees of freedom in the denominator of t, which is n by p. So you need to consider both there. And I'll just tell you that this null distribution of W turns out to be f with numerator degrees of freedom as P2 and denominator degrees of freedom as n minus p. Okay, so this is very similar to the t distribution. In the t distribution here, the numerator degrees of freedom is just 1 normal random variable, right? But the denominator has n minus p. So that denominator n minus p comes to the denominator degrees of freedom f. But in the numerator of f, since we have P2, how to say, dimensions in the beta 2 hat. So basically beta 2 hat has P2 dimensions, and each dimension is standard normal. So that can explain why we have P2 in the numerator degrees of freedom. So even though I'm not doing the full derivation to justify this F distribution, but I'm trying to say that this is the intuition there. Oh, one more thing I forgot is that we need W divided by P2 to follow this. The reason is why. In the definition of F distribution, we need to have two independent chi-square random variables, each divided by its degrees of freedom. So basically, we need to have chi-square P2 divided by P2 over chi-square M by P divided by M by P. So this is a ratio that follows the F distribution. And more importantly, this chi-square P2 and chi-square M by P must be two independent random variables. So in our construction of the W, we need to divide P2 to satisfy its ratio form. So that's why we can say W divided by P2 is approximately this F distribution. It's actually exactly this F distribution under the null if our model for linear model is the normal linear model. That is epsilon follows normal, zero mean, sigma square I as the covariance matrix. Okay, so this is the null distribution. But as we like to talk about asymptotics, when n gets large, what happens? Because you see that on this side, when n gets large, then we need to let n by n minus p be something, right? We cannot just keep as n minus p because n is in the right-hand side. So I'll just say quickly that as n gets large, okay, for the t statistic that follows t n by p under the null, this will converge to in distribution to standard normal. So this is a known fact for t distribution. As the degrees of freedom gets larger and larger, the t distribution will converge to a normal distribution. And when n minus p is small, then the t distribution will be obviously more heavy-tailed than normal. So that is another known fact to be good to know. And for F distribution, okay, so I can say that this W, okay, is under null is following, I'll just multiply P2 to the right-hand side. P2 times an F distribution with P2 n minus P as the 2 degrees of freedom. And as n gets infinity, close to approaches infinity, this n minus p approaches infinity, and this p2 times f distribution will actually converge to a chi-square distribution with just p2 degrees of freedom. Okay, so chi-square is like an asymptotic form of f multiply its numerator degrees of freedom, while standard normal is the asymptotic form of t distribution. Okay, so as long as we can compute this Wald statistic on our data using beta 2 hat and our plugin variance covariance matrix for beta 2 hat, you plug in the sigma square hat. Then you can compute p-value as the right tail probability for F distribution, because F distribution has the support just from 0 to positive infinity. You have the right tail as the p-value. You compare that to your significance level. Okay, that's the Wald test. And in parallel to Wald test, okay, same for this sub-vector testing question. Maybe I'll mark Wald test as approach 1. Approach 2 is more general. It is called a likelihood ratio test. Okay, often written in short as LRT. So the likelihood ratio test is not specific to linear model. It is more general than that. It can be used as long as you have the so-called nested models. So one model is smaller and nested under a bigger model. Sorry, I think I have something right here. I think it's sort of disconnected. Let me see what happens. Let me just pause the recording a little bit. Now it's back home. All right. Maybe resume the sharing. All right, can you see my screen now? Okay, so for the nested model, essentially, when we write this null hypothesis, the same one, beta 2 equals to 0, right, vector. So the model has only parameters of P1 dimensional. So basically, the linear model is essentially y equals to, I would say, maybe x design matrix with the first P1 columns only, 1 to P1, as a submatrix with the first P1 columns times beta 1 plus epsilon. Okay, so this is so-called a reduced model. Reduced model with P1 predictors only. All right. So this is so-called reduced model. While under the alternative hypothesis, beta 2 is not equal to 0, then we can have the full model, x beta plus epsilon. So this is called a full model with P predictors. And as the P1 predictors are included among the P predictors, we say the reduced model is nested under the full model. So this is what we mean. Nested under the full model. Okay, so the likelihood ratio test is a very general form that focused on a likelihood ratio. So likelihood ratio is called this big lambda, written as the big lambda. It is the ratio of two maximum likelihoods. So first one is that we call the likelihood L beta, right? Big L as the likelihood function. But we're considering the maximum likelihood with beta constrained to the case of beta of H0. That is, we force beta 2 to be 0, and we only find the values of beta 1 to maximize the likelihood. While that's the numerator, the denominator is the unconstrained one. That is, we just maximize beta in the full domain, right? Whatever value that's allowed for beta. In this case, it's RP, p-dimensional Euclidean space, L beta. That's called likelihood ratio. So if I just ask you which value would be bigger, the numerator or denominator, what will be your answer? It should be the denominator that is bigger, right? Because when you do the maximization, you have more choices. So you should have a bit larger value to achieve. So then, knowing that is the fact, then the likelihood ratio test is trying to assess, we know this ratio must be less than 1, but whether it is small enough to let us conclude that this small ratio, less than 1, indicates that the full model under the alternative hypothesis is really better than the reduced model. So that's what we want to conclude. Because we know there will be a difference. and the ratio cannot be equal to 1. But we want to say that this difference between the ratio and 1 is nothing more than just the randomness in our data. Because for any data set, you would always have such difference such ratio less than 1. But whether that is something significant to indicate the reduced model is not as good as the full model. That is the question we want to answer. Okay, and don't forget that we actually have written out the linear model likelihood. Let me try to find that. This is what we have there. Okay, a recap. This is the likelihood form. Essentially, we wrote it in this way. And you can see that if we take the log of the likelihood, what would be nice is that we can get rid of the exponential term, and the exponent will come down, right? So we will have the log likelihood with something here plus, or actually minus, this square loss divided by 2 sigma square. So that is something we hope to achieve. So basically, in the linear model case, in the linear model with normal and homoscedastic errors. So in that simpler setting, we actually have this log likelihood of beta. We just keep the term, this only term related to beta, because sigma square is not the parameter of interest for now. So this L beta can be written as some constant minus 2 sigma square. And over here, we have the summation yi minus xi transpose beta square, right? This is the log likelihood, and we use the small l to mean log likelihood. And we know that by maximizing this log likelihood, it is equivalent to minimizing the square loss, and that is the OLS, ordinary least square, and then we get a beta hat, right? So basically, using the OLS beta hat, we can write the log likelihood of beta hat is essentially some constant minus 2 sigma square. And in the numerator, it is the sum of EI square, residual square. Well, we get the residual. And if you remember last time I told you, the sum of residual square has a name called RSS, residual sum squares over 2 sigma square. So assuming that we consider sigma squared to be known, okay, don't worry about Newton's parameter for now. Then once we compare 2 beta hats, the parameters in terms of log likelihood, we should actually be comparing the 2 RSS. So in other words, I'm saying that if you look at the likelihood ratio here, if I take the log of this likelihood ratio, essentially I'm getting log max, or maybe I should say max beta under H0 of the log likelihood minus max without constraint under the alternative of the log likelihood. I'm comparing 2 log likelihoods, okay? And if I assume that a constant with about the same sigma square can be canceled out, and same denominator here, what do I have? Essentially, I have minus RSS obtained under the null model over 2 sigma square minus RSS under the alternative model, the full model. I'll just drop the subscript, mean the full model over 2 sigma square. Okay, and because of the minus sign and because of the 2. So basically, this thing, as I know, the lambda is less than 1. So log lambda would be negative. Okay, log less than 1 value is negative. And we know that we don't like our test statistic to be negative. Because of that, we want to multiply a negative sign here. Also, we want to multiply 2 to get rid of 2 from our denominator. So this comes to like LRT statistic defined as -2 log lambda, okay? And that will just be, for linear model, is just RSS H0 minus RSS divided by sigma squared. That's the log likelihood ratio test statistic. And also, since you know that under the reduced model, you will not fit the data as well as the full model, because the full model has more flexibility to fit your data. So no wonder that the residual sum of square under H0 will be bigger than the RSS under the full model. So that's why you will have a positive difference in the numerator, and you will have a positive test statistic. Okay. And again, we need to consider that sigma square is unfortunately unknown. Then we need to plug in, right? How do we do the plug in for this nuisance parameter? So this is a question I have for you to think about. The question is, how do we estimate sigma square? Should we estimate it under the full model, under the alternative hypothesis, or under the reduced model, the null hypothesis? Which way should we estimate sigma square? Okay, I think the answer here is a little bit tricky, but it depends on, I think this is something we need to always have in mind in our classical statistics or statistical inference. That is, what do we think as the true model? That's the key thing. So I would say that under the true model, you assume to be y equals x beta plus epsilon, which is our full model. If you assume this to be our true model, then sigma square hat should be RSS under the full model divided by n minus p, our unbiased estimate in this case. So in other words, when we use this sigma square to do plugin, the true model we have in mind is the full model. And we're considering the null hypothesis as the reduced model just as some candidate. We're trying to see whether we can reject it. If we do, then the null model is out, where we don't consider it to be a true model. But if we don't reject, then the next question is, should we go to the null model and then use that reduced model as our true model for our inference, right? I think that's the next step question. So that's why I would say in practice, the statistical inference decisions are usually sequential. You're not just doing one inference and you're done, but you should do it sequential. So sequential analysis is another important topic in statistics, even though it's not a focus of this class, but I just want to bring this to your attention. So this is one philosophical way to justify we use this sigma square, because we're still thinking of the true model as the full model. But besides that, I would say in the practical way of thinking, using this sigma square, not this sigma square hat under the null, if I write it as RSS H0 n minus P1. Yeah, if we're not using this, it's because, you know, if we have the null model fits the data less well than the full model, then this sigma square hat is likely bigger, right? You have a larger sigma square hat. And having a larger sigma square hat will make the likelihood statistics smaller. So being smaller means that you are being, how to say, you're being more conservative. You're being more conservative because you want to reject the null with a large statistic value, right? So for that reason, you can justify, okay, by using a smaller sigma square hat here, I'm more likely to have a larger test statistic, and there's more chance that I would reject my null. Okay, reject my null means that I go with the full model. So basically, using the true model as your using the full model as your true model in mind, you are inherently favoring the true model than the reduced model. So again, this is another thing to see the subjectivity in statistical inference. Furthermore, we have to derive the theory. Okay, what is the null hypothesis or null distribution for this statistic under the true model? So basically, we're deriving that null distribution under the true model. And so, okay, I'll just cross out this, and I will say that we can show that this -2 log, I will put hat here to mean that we plug in sigma hat squared, defined as RSS H0 minus RSS divided by RSS over n minus p. That's the denominator. So we can show that this would follow, again, asymptotically if you don't have the normal assumption. But if you do, it is just exact chi-square distribution with P2 degrees of freedom. And this P2 is the difference in degrees of freedom between the full model and the reduced model. They differ by P2 parameters. So this is what people use in practice. And likelihood ratio test has become a very easy to use general method because you can just calculate likelihood ratio, take the log, multiply by -2, and then use chi-square distribution whose degrees of freedom is determined. It's just the difference in number of parameters between the two models to get a p-value, and then you're done. Okay, so you see that it is not exactly the same as the Wald statistic because you have a different formula for test statistics, right? But it has very similar asymptotic distribution, that is chi-square P2, because if you go back to the Wald, right, Wald also has chi-square P2. So therefore, in practice, it can be shown that you can empirically try both approaches and see how big their differences are. In many cases, especially when your model is just this normal linear model, their differences won't be that big. So, but likelihood ratio test, as I said, it's more general than the Wald test because Wald test is specific design for a linear model, while likelihood ratio test is beyond linear model. Okay, so that's all for today. We have the time up, but next time we will talk about a third approach besides the Wald test and likelihood ratio test is the so-called ANOVA. So ANOVA is also more general than, I would say ANOVA is more general than Wald test, but it is still under the linear model setting. Okay, so for ANOVA, what you can do is that you can go beyond just comparing two models, a reduced model and a full model. You can have a sequence of reduced model in the middle. So you can do the thing called hierarchical ANOVA. Maybe you can consider adding predictors one at a time and see where you want to stop. So we'll talk about ANOVA in our next lecture. But for now, I hope you can review the materials we covered so far and bring your questions to the beginning of our next lecture. So then we can discuss your questions. Okay, so that's all for today, and I'll see you on Wednesday. Okay, thank you. Thank you.
Thank you.
Bye. Thank you.